Yes, as you can see.
Okay. So, do you have any question from the last lecture? So, did you find the time? I also uploaded lecture number 3 already, and then I will upload also this one in the next days. I don't know if someone had time to think a little bit the things we discuss, and you have questions. No? Okay. So if you remember, we were discussing a little bit about how to estimate the underground profile. So a couple of lectures ago, we indicated that with H over V was possible to estimate also the underground structure, but unfortunately the H over V suffer of trade-off between thickness and velocity. So I show you this example that was with two different models in terms of velocity in the sedimentary cover and velocity in the bedrock were producing the same H over V. So you don't see this difference. But last time we also introduced the method working with arrays, and we immediately see that the dispersion curve can have a different sensitivity with respect to the H over V on the underground structure. And therefore it was worth combining in the inversion the dispersion curve and the H over V, because the H over V, we said it's very sensitive to the boundary, so to the impedance contrast at depth, while the dispersion curve is mainly sensitive to the velocity in the sedimentary layer. So we can imagine that if a velocity can be fixed a little bit from the dispersion curve layer, then with H over V, we have a possibility to solve some information about the thickness. So it makes sense to invert them simultaneously. We also said that in some cases, we can also use the love waves, because in most of the cases now we are working with free component sensors, and the free component sensors offer us the possibility to record also transverse ground motion in the horizontal component, that with a different approach, I show you the original one of Aki, always based on the correlation coefficient for the three different components, that was possible to estimate also the love waves velocity, dispersion curve, and combining in the inversion Rayleigh, love, and H over V, it's possible to improve even more the final model of the underground that we can retrieve. And the reason was shown in this matrix. You see these matrices, we see the sensitivity, let's say, of the Rayleigh, of the love, and the H over V waves to the underground structure. And we see that it's completely different. So it means that when we merge in the joint inversion the information coming from the different curves, we can better distinguish amongst the many models that can be maybe can produce similar results. For example, for the H over V, we can distinguish the one that has also features that are only similar for the Rayleigh or for the love waves. And that was the case. In the last year, so we said it was possible to estimate quite reasonably the velocity. In the last year, some attempts, I will not enter into much details of this, but it's good that you know it. Using also seismic noise, there are some attempts to estimate not only the velocity of the underground, but also the quality factor, so the attenuation in the underground. And that's what we proposed a few years ago. So we started with studies at large scale, so at the regional scale. but then we adapted also at a relatively small scale, so for our small arrays. Of course, things can be a little bit different because the quality factor can be relatively low for sedimentary cover. We are talking about frequency contents completely different from what we have at a regional level, but we show that it was still possible to estimate the quality factor for the shear waves also using seismic noise. Again, we were making a modification with respect to the original assumption of Aki. Aki was expecting that all the waves were propagating in an elastic medium, so that the attenuation was playing a small role because the distance between the sensor was small. But when we are talking a small array in our soft material, the attenuation can be also relatively strong because the material is very soft, like lace or sands and so on. So it was shown that therefore the correlation coefficient for one frequency and as a function of distance are following a Bessel function, but the Bessel function is then damped, let's say, by an attenuation factor for, in this case, Rayleigh waves. So it's an attenuation factor alpha and a distance r. It's the distance between the two sensors. And this attenuation factor depends on omega, so 2pf, so on the frequency. It depends on the quality factor for Rayleigh waves and on the phase velocity of Rayleigh waves. The phase velocity from the dispersion curve, we can obtain it as well as the alpha coefficient then in a sort of grid search procedure, which is modified with respect to the original approach. So in this case, we will test many Bessel functions for each combination of distance and for each frequency, for different phase velocities, like we have done last time, but also for different factor alpha. So our grid search will not be anymore only function of a velocity, but will be function of velocity and of the attenuation coefficient. So you see some example here. The dashed line was the original curve, or let's say the fitting without considering attenuation. The gray line is the fitting considering attenuation. You see, especially for the points which are more far away, there is some better improvement or some improvement in the fit. In this case, we see the results as a function of velocity. You remember like our curve with the minimum last time. So this is the RMS of the difference between the best or the tested Bessel function and attenuation coefficient in 2D. So we see this difference between all the models that we test. It's clear that for 3.25 Hertz in this case, we can again constrain very well. There is no velocity changes with respect to the original one without using attenuation. This is the triangle. And the quality factor or the attenuation is reasonably identified. So there is a small variation. There is a quite a clear minimum also as a function of alpha. When the frequency is increasing, the velocity is still relatively well estimated, and you see it very well because there is a very narrow band of RMS, let's say, in the direction of velocity, but the attenuation start to be, let's say, affected by larger uncertainties, and their uncertainties are becoming very, very large when, let's say, we are working with high frequency. This is because you have a sort of flattening of your combination of the curves. For the high frequency, also on small path, you lose easily correlation. One part is, of course, related to the damping, but when you lose it, then every value of Q or high alpha is able to reproduce you more or less the same behavior. Okay, so these are the alpha that we measure, alpha value that we measure, and this after the inversion, how we can retrieve it. So let's say in this case, we can make an inversion not only for velocity, so starting from the dispersion curve, but also for these black dots that are representing the attenuation for the Rayleigh waves. We know that this alpha coefficient depends on the frequency, on the velocity, and therefore we can calculate also the quality factor of Rayleigh waves. And this is how it looks like. And you see that this quality factor, which is relatively low, in this case is a little bit above 5, has also quite a strong frequency component. Okay, but now we have phase velocity, so our dispersion curve. We have the attenuation coefficient and the quality factor for Rayleigh waves, but as usual, I want the shear wave velocity of the underground, and I want to have the quality factor for shear velocity, the profile of the underground, because when I will make a numerical simulation of ground motion, the quality factor is a quite important parameter. So how this can be done? The velocity can be obtained in a separated way, and we saw last time that we can do it by inversion. For the quality factor, we can come back to some relation that is linking the underground structure with the attenuation of the factor of Rayleigh waves as a function of frequency. So we know from theory that this attenuation factor depends on the phase velocity of Rayleigh waves. It depends on the VP velocity indicated here in each layer of the underground interested by the propagation of Rayleigh waves. It depends on the quality factor of P waves in the underground, and in the similar way also on the shear wave velocity and on the quality factor for the shear waves. Again, here you see a partial derivatives where we see the variation. It's the same partial derivative matrix that we have seen last time, but is giving us information about how much the phase velocity is changing if I change the shear wave velocity or if I change the P wave velocity. Okay, this is simply a linear system of equation. In some of the cases where, for example, medium is not saturated, the effect of VP is becoming negligible. So this part of equation can be neglected. So for sake of simplicity, now I show you that what remain is this term, omega divided 2c omega square, omega c square omega. These terms goes away, and only this summation is remaining. And this again can be described as a sort of linear system where my data are the attenuation factors that I calculate for each frequency in the way I showed you before. My matrix, my kernel will be determined by these terms. So I will have a first line relative to the first frequency, where I will have a partial derivatives for the velocity of the first frequency with respect to each layer in the model of the underground. So E from M are the models, the number of layers in the underground. And this each line is for a different frequency, and each column is for a different layer in the model. What are my unknown? Unknown are, of course, in this case, the quality factor. Here I'm considering only shear waves. The quality factor for shear waves in each layer from 1 to M in my underground structure. This is, again, a linear system, and I can solve the linear system very simply. For example, using a least square method or very similarly to what we have seen for the dispersion curve. So that's again our matrix that is telling us for layer 1 to 5, from 6 to 10, the partial derivative matrix for the different frequencies in dependency on the V and QP, and from 6 to 10, the dependency on VS and QS. And you see immediately that, as I mentioned before, in many cases, the dependency on VP and QP is very small. So we have mainly an influence of shear waves and QS also on these partial derivatives, and therefore on the resolution that we can obtain. From this, you can also immediately observe that in the shallow layer, so 6 is the most shallow layer, and 7 and so on is going deeper, we have the largest partial derivatives, the largest value. When we go deeper, we lose resolution. So we also have to select the ad hoc number of layer for inverting. So in this way, it's possible also not only to obtain 1D velocity profiles for the velocity in the underground, but also for the shear wave quality factor. This is still a method that it didn't become yet, how can I say, standard. We are still working on it. We have, for example, here now a PhD student working in improving the method of inversion. We had also many test case studies where we tested the method and we could compare the results of the quality factor obtained in this way with the quality factor obtained with other ways. And the results were quite positive, and in some cases also quite interesting, in the sense that reevaluating, especially for soft material, the quality factor, we observe that the generally made assumption that higher velocity corresponds also to higher quality factor. For soft material, sedimentary material, it's not a must, let's say. It's not always like this. So for example, you can have a relatively high shear wave velocity material like gravels that can have also some low quality factor. And this is because while the shear wave velocity is mainly related to the stiffness of a particle of your material, so and therefore maybe gravels or boulders can also have a very high stiff material, so the velocity at which the perturbation is propagating is high, the contact between the grains can be quite loose, so the perturbation cannot propagate efficiently, and there is a lot of transformation of energy for friction or other reason at the boundary of the material. So that was one of our results, and now we are estimating and checking for more and more places where to make analysis, validate the results, make comparison. And but the results also recently, similar results have been found in California by Dave Poor, who was observing a similar behavior with shear wave velocity not directly correlating with a quality factor. And that's exactly because the nature of the two, let's say, parameter can be quite different. So they are sensitive to different physical parameters. So this is quite innovative, but I have also to tell you that that's the major problem that we have inside response analysis. So while I would say that for the shear wave velocity, that is the main parameter of our interest, at least for what is the use that we are aiming at in our field, I would say that we can nowadays obtain reasonable results that can be used then easily in numerical simulation. I would say that we cannot say the same for the damping or the quality factor. So there is still a lot to be done before we can say that we are really able to estimate a good quality factor to be used in numerical simulation. And you have to imagine that the effect of Q is dramatic in numerical simulation, because a change in Q that is not well constrained can strongly change the amplitude of a ground motion and also the duration of ground motion in a quite, I would say, significant way. So this is really an important point that has to be taken into account. So any question about this? No. Okay. Okay, I mentioned that we were considering in the ray methods mainly that the velocity below the ray, so our velocity structure, is homogeneous. So we are not considering, when you use this method, that the velocity is changing laterally below the ray. That's the major assumption. We know that in certain cases, this is of course not true. So there could be the reason to consider only small arrays, for example, and we can consider in locally under a small part of the array that the structure is 1D. We can therefore estimate a 1D profile, and then moving this 1D profile for the different part of arrays, one can obtain sort of cross 2D cross section that are showing also the lateral changes. This was one part of a work that we have done many years ago, where we are introducing, for example, the interferometric approach that we will see later to estimate in each point a sort of dispersion curve, and then to obtain a pseudo 2D profile for the underground structure. And this, you see here, was also calibrated in a place where we knew from independent measurement, geophysical measurements, a little bit about the underground structure. This is an example of geoelectric results, but we have done it also with, with georadar. And you see that there is a good consistency between the changes in the shallow velocity structure with a clear boundary at around 20 meters, that then it's increasing, and then there is a jump in the velocity. So I will show you a little bit of this interferometric approach, but because in a sense, this will come back a lot for people working at regional scale in seismology, for people working at the small scale, and also working in building structure, because we are using the same approach also in building structure to estimate the velocity of propagation of waves also in the buildings. So I will give you just some basics. So the idea, as I mentioned here, is that it's starting from the Claerbout's conjecture. So he was mentioning that cross-correlating noise traces recorded at two different locations on the surface, one could reconstruct the wave field that would be recorded at one of the location if there was a source at the other location. It's just like if you imagine you are in the position where you have a hammer, you send a source in the ground, and you have another sensor recording this pulse. So the idea is we don't have anyone with a hammer. We just have two stations recording noise coming from everywhere. If I just cross-correlate all the signal, like we have done also with the hacking method, if I don't look at these, let's say, by the correlation point of view of the maximum, but I just look at its shape, this wavelet that I obtained by the cross-correlation correspond to the green function, so to the propagation function from one sensor to the other. like if someone was just sending an impulse in the ground in the first position and recording it in the other position. So the method you see again here, we have two stations. This is a signal as a function of time. This is simply our correlation function between the two sensors that you remember. This can be also calculated through the Fourier transform of the two signals. And then it was shown that the time derivative of this cross-correlation function was related to the time domain green function between the two medium. So it was possible then to obtain just the correlation function and the green function, the propagation from one sensor to the other. Of course, since you have two sensors, you will have, let's say, two pulses generally. One describing the propagation from this sensor to this one, and another showing the propagation from this direction to the other direction. So we will have always two parts, one which is acausal and one which is causal. So one with negative time and one with positive time. So here in the figure, we have two stations placed on the ground, and we imagine that every one of these points, these gray circles, are representing a possible source of noise that is generated at different time and you see in different position. If I take the cross correlation of all the signals, of all this noise, and I stack it for a long time, I expect to find, yes? Hello? Hello? Someone wanted to say something? No, okay. Maybe it was a mic, but by chance it was open. So if you take the correlation of all the signal between station 1 and station 2, using station 1 as a reference, we will observe after stacking two pulses, two signals in our recording. One will describe the propagation from station 1 to 2, which is this one, it's the causal part, and one very similar if a distribution of noises is nearly identical, is homogeneous, will show the propagation of a signal, let's say from 2 to 1, in the causal part. What's happened if the distribution of noise is not so homogeneous? Okay, let's assume that most of the noise sources are located nearby, let's say, the area of station 1. In this case, what we will observe is that the arrival time of these two signals is the same, but the amplitude can be different. So the causal part will be much bigger in terms of amplitude, the causal part. But you see, still only the amplitude is different. The arrival time is still symmetric. If you invert the situation, the distribution of noise will tell you that we will have, again, something asymmetric in terms of amplitude. If most of the noise sources are located by this side, we will have the causal part that is becoming bigger. Of course, if we invert in the correlation the sense of a correlation, also the image will be automatically flipped in the same way. This is also opening some question, how good should be the distribution of noise to retrieve a green function without any, let's say, big bias. And some studies have shown that if there is a sufficient azimuthal coverage, maybe it doesn't have to be complete, still we are able to retrieve reasonably this travel time. Some methods of analysis of noise have been proposed and became some standards. Some of them were simply a reproduction of very old methodology. For example, the time domain normalization, so the 1-bit normalization, is nothing else that what already at the time of Aki they were using, but they were using this simply because it was too complicated at the time to work with a signal that was not simply binary. And many others, like spectral whitening, has been introduced, and now there is some discussion if they can even create some problems to the analysis or less. So the method has found in the last years a huge amount of application, from surface wave tomography at global and regional scale, where it was quite, let's say, obvious to apply because you have a huge amount of noise recording from everywhere, but especially the propagation over very long distance for the low frequency waves can be very efficient because the quality factor for the low frequency is quite high, so there is not a lot of attenuation. Then I mentioned estimating the building response. We use it a lot also for studying the propagation of waves in buildings, but also in the underground, just around the buildings. It was used in seismic for ground roll estimation and removal. So generally in seismic, one of the problems, you want to look at reflected waves, for example. So you want to get rid of surface waves. And in this wave, you can remove some large amplitude signal that is masking, for example, important arrival for imaging, or retrieval of reflection, and also in other methods like control source electromagnetic methods. So these are some examples of the first studies you see 15 years ago, where the people started looking at the possibility of making even tomography, studying the underground using this approach. And that was very interesting because there was an important point that the data from a larger and larger number of stations at global level were growing, and especially were available more and more in continuous. So we could really use the all data, including the seismic noise recorded by stations around the world. And you see here that these are just some correlation of the ZZ component for different frequency band. And you see that in some frequency band, you can better recognize, for example, a P wave arrival, so the direct waves, and then later the surface waves. In this case, since we are talking about the vertical component, the Z component is mainly Rayleigh wave. What is interesting here is also that you can immediately see that the noise sources are not distributed homogeneously, and you immediately see because we have a clear, let's say, stronger right side than the left side. Of course, like in every method, then when you have images like this, you can measure, you know, the time and the distance at which the waves arrive. So you can measure their travel time, and you can use the travel time estimation like in any tomographic methods. So in tomography, a little bit like you remember the first inversion example that I show you for the block, where we were measuring the travel time, we could measure the velocity. Yeah, you can, of course, do the same also with the travel time of the waves generated by an earthquake. If it's not an earthquake, we can still retrieve the travel times of waves that are, in this case, related to seismic noise and describing the propagation between two different stations. The question at the time that we had was, okay, it works fine for huge amount of data collected by global networks. It's where we know also that waves can propagate for a very long distance. I guess you remember when I show you this noise spectra recorded in United States from Hawaii to Colorado. you could still see the peak of that noise at at very large distances from the ocean. So you have thousands of kilometers of propagation in a very efficient way. So the question was, okay, can we see the same in shallow material where we know that the wavelengths are much shorter than the one that we consider at global level? And therefore, they make more cycles, they will attenuate faster, so we will lose them before, especially considering that the shallow material has a very strong attenuation. We saw before quality factor in the order of 10, not of 300. So we expect that there is a lot of probability to lose the signal, let's say, over a very short distance. So we decided then to make some analysis, and we focus on this area that I showed you before. So generally, you can imagine the standard was to work maybe at European level, international network, looking at distances of hundreds of kilometers, estimating the velocity profile for tens of kilometers, and working at this period, so it's 20 seconds, so 0.05 hertz, so very long wavelength. And we wanted to scale this to a much smaller distance, so we are 30 meters, a depth of nearly 20 meters soft material, and therefore also working in high frequency range, not 0.05, but maybe 5 hertz, okay, 100 times bigger, or something like this. So we deploy the instrument, and we also look, that's important, for a site where we knew that there was a discontinuity. So where we knew that the standard 1D method that we have seen last time might have problem in retrieving a single, let's say, velocity profile, because the velocity is changing laterally. So I was violating one of the main assumptions that we were doing. So, and that's exactly what we assume. Generally, the 1D method assumed that below the array, the structure is 2D. At that time, luckily, there was an interesting study of Liu et al. In 2008, who showed that the velocity estimated between two stations, so they made some profile. You see there is between the red line and the green line, there is a clear jump, a clear step in the bedrock, 5 meters, so with a clear lateral change of velocity. And the first question was, okay, can we, with arrays, see the effect of this lateral change? And the answer was coming from this dispersion curve. So if you focus on an array only based with sensor along the red line, you would obtain, let's say, these dispersion curves with some differences depending on the offset between the source and the receiver. If you go to the green line, you will observe something completely different. You immediately see that for already relatively short wavelength, the velocity is tending to increasing much more. This is because we start to see, let's say, this higher velocity here. If we combine the sensor of red and green line, we will obtain a curve that is something in between the two events. So using the whole spread, it's clear that still we can keep some information on the average velocity from here to here. So there is a chance that we observing our velocity, our Rayleigh wave velocity, we get some information on the lateral heterogeneities on the underground. So we deployed the sensors. You see every circle is a sensor. This cross-section corresponds to this dashed line. So we made a standard experiment with our sensors. So we let the sensors running for 2 weeks. And this is the georadar, you see, section that clearly show something very similar to what you were observing before. You can also imagine that it's very stretched. So this 20 meter, this is 100 meters. So take also this into account when you look at the images. So we let the noise running, the stations running, we record the noise for 1 week. And then having a lot of noise, we said, okay, we would like to see if we calculate the cross correlation between each pair of stations, after how much time the cross correlation function, so this indication of the propagation of waves, is becoming stable. That was important because if the idea was to use these methods in urban areas, we have to be sure that we could have good results in a short period of time. In an urban area, we cannot leave an array like this for 1 week in the middle of a street. It would be impossible. But here we could, so we could have plenty of data in order to check what was the minimum number of recording that was necessary. So we did it, and then we start calculating the green functions, and we check how much they were changing over the number of windows. Each window was longer 30 seconds that we were stacking. And you see that as soon as you stack the values, or you average many windows, there is a rapid decrease of RMS, so it means increase of quality, but after some windows, there is no improvement anymore. So in general, we observe that at this site, after nearly 20 minutes of recordings, we were already having reasonable results. And that was a good point, even if we let the stations running for 1 week in the field, so much longer, but 20 minutes were sufficient to obtain reasonable results for our study. This is how our signal was looking at. So we make analysis on all the components of motion. So on the vertical, the radial, so in the component that was oriented between the two stations, and also in the transversal, so the component orthogonal to the propagation, to the direction which you can link the two stations. First, we wanted also to be sure that these waves, which kind of waves we were dealing with. So we just made some polarization analysis, and we observed that our main wavelet had some elliptical polarization, like we could expect for Rayleigh waves, but the ellipse was tilted, and this kind of tilting was shown to be quite typical also for Rayleigh waves due to a high level of attenuation in the material. So the attenuation is playing a role in further shifting the two signals. So now we knew that we were dealing with Rayleigh waves, and we could then try to plot, let's say, the results of the cross correlation for each couple of stations that we were measuring as a function of distance between the two stations. This is an example when we filter the results at 14 Hertz. And what you see is that, okay, again, we see that one branch, it's more or less symmetrical to this one, but that's clearly smaller amplitude. We also could follow very well then this velocity. We applied the FK techniques that we discussed last time. And with the FK, you immediately see that you can recognize that most of the noise is coming from the southwestern direction with respect to my array. And that's why we have also this asymmetry. So the source of noise were not homogeneously distributed, but as I showed you at the beginning, since they are not homogeneously distributed, they generate some asymmetric green function in terms of amplitude. And 14 Hertz is quite shallow. And we said, okay, let's just plot the delay time. So we said, okay, we have an average velocity here that we can assume just fitting the data. And we calculate for each one of these distances the difference of the residual as a function of also the back azimuth from which this combination was coming. What you observe is that the delay is generally increasing. So the delay or the travel time, you can see it in this way, it's increasing when I increase the distance, which is reasonable. And I do not observe, depending on the azimuth, a clear change with the azimuth. So more or less, it's like if my medium is homogeneous for 14 Hertz. If I repeat the same with 6 Hertz, you can immediately see that first is much more symmetric. And this is also what the FK spectrum is telling me. It's telling me, look, I have energy coming mainly from every direction. But when I do the same with the scattering, I see that the distribution is not so homogeneous anymore. So there are azimuths from which I can see, let's say, faster, slower, let's say, or faster arrival. So it changes with respect to other azimuth. And 6 Hertz, if you remember, it's a longer wavelength, so it's going deeper. So, and this is how the travel time look like for the 6 and for the 14 Hertz. So this is an important information. Just imagine what is telling me this first result. It's telling me that 14 Hertz, which is propagating in the shallow part, see everything homogeneous. 6 Hertz, which is propagating deeper, see that below there is some difference. And that's an important information. So it seems that when I investigate it deeper, I can see some discontinuity. So we try to solve a problem as a standard linear tomography problem. So in which this is exactly the same that we have seen in the inversion procedure. You see the travel time for each path between the two sensors is simply the sum of the propagation along the line in each hypothetical block, like we have seen last time, multiplied the slowness in the block. And then I sum up for all the different paths in each block. So it's just the line element along the ray path. And this equation, as we have seen last time, if I do it for all the possible travel time, is becoming just can be written in a matrix form where T is just the travel time that I'm measuring for each path. L is a matrix where I have that is describing all the paths. So we'll have M rays, which are my data, and N will be the number of cells. And S is the slowness, so the inverse of velocity in each one of these N cells. So given my data travel time that I measure, given the matrix of ray path segments that I can simply geometrically calculate, we are making a linear assumption, no? Like we have done in the first description of inversion last time. What I want to calculate is the slowness in each one of the blocks. Okay, we had to do some, to find some solutions. So we did it also making some weighting for the data and so on. This, maybe we can skip it. Also, we were weighting the fact that it's very important that the rays are not crossing the cell always in the same direction. Otherwise, we are not able to distinguish the velocity changes. It's very important that the rays are crossing the cell from different direction in order to better distinguish the lateral variation. And therefore, you can also weight in a different way in your inversion each cell depending on the distribution of the rays within it. Okay, there was some smoothing and so on. I will not enter into all the details of the inversion. But at the end, So if someone is interested, of course, can contact me and we can discuss it. But the main point is exactly what I was showing today to you. So if we do the inversion, then this, you remember, can be like the block of last time, but seen from above. If I see how the velocity is changing for 14 hertz, each dot you see is a station, and these are the rays connecting all the possible combination of stations. So I'm just looking from above. If I look at the velocity changes of 14 hertz, I don't see so much. Only some problems here, probably related to the paucity of data you see and the very bad coverage that we have here. But in general, I have a very nice blue everywhere. So for a high frequency propagating only on the surface, remember lambda depends on the velocity divided the frequency, everything is more or less homogeneous. If I use a lower frequency, which is going deeper, I start seeing some differences. So this part, the southwest part, is showing lower velocity, while the velocity is increasing in the northeast part. And in green, this is the velocity profile that I have. So as I mentioned last time, for each one of these blocks, I can have the velocity for 14, for 6 hertz, and so on. And therefore, in each one of these points, I can also calculate a 1D velocity profile. And when I will put all these 1D velocity profile together, I will have a sort of pseudo 3D. So we also check with some synthetic data. So we generate surface waves, and depending on we have a model that you see, for example, a checkerboard or another model in this way. And we try to see with this geometry how much we could resolve. And we observe, okay, in a model like this, I could resolve it in this way, which is quite good, and the same for this other model. So we made some tests of reliability, let's say, of our results. We also check with Bootstrap, so statistical analysis, how robust were the results. And when we were convinced that everything was working, we went on and we did exactly what I showed you before. And astonishingly, with just a few minutes of seismic noise, we were able to obtain a structure of the underground that has let's say, a very strong similarity with that was obtained with our geophysical methods. So now we are using more and more, not only us, many groups, also seismic interferometry on small scale, because it's a powerful tool also to estimate the underground structure, even in areas where probably active methods would not be completely feasible. Okay, do you have questions about this part or curiosity? I would like to have some more questions today before going on, because we finish mainly all this part of noise, and I think it would be good if you have questions or something that you didn't understand or curiosities. Please let me know. It's very important.
I have question related to the previous slide.
Yes. This one?
No, the previous one.
Tell me when to stop, okay?
The first one where we have the coverage of difference of first and a different frequency. The previous one, this one.
Ah, okay. Yes.
Not this one. Okay.
This one, another one?
No. The where we have a difference of maybe we use the 6 hertz frequency and 14 hertz frequency.
Sorry, I didn't get the question. Can you repeat?
If you go ahead, I will ask you to stop there in the slide.
Okay. More?
The next one, yeah.
This one?
No, the next one where we have the coverage of the data, the lines where we have shown. The next one. The next.
Okay, I think I'm going in the wrong direction.
Yeah, maybe I think so.
This one, you mean?
No, it was very near to the where we have ended it. Yeah, this
So,
one.
uh,
Yeah, you
okay.
are in. So you have choose the 14 hertz frequency and uh,
Are you sure it's this?
no, the inversion results where we have the inversion results.
I didn't get it. So which one do you want to see a slide?
Where
Before?
we have bins of the inversion results at the 6 hertz frequency and 14 hertz frequency.
Okay. This one.
I think yeah, this one, 139, yeah.
Okay, great.
Uh, and you have used the 14 hertz frequency and 6 hertz frequency where we are using the noise data, right?
Yes.
So if we go for the 14 hertz frequency, is it feasible to use that much high frequency for the noise analysis?
Yes, in principle, yes, you can do it, but you can also go to very, very shallow, maybe for smaller distance, because then you will lose the signal um, before.
Mhm.
But it depends how deep you want to go. So 14 hertz,
Yeah,
just make a calculation. You are nearly, I just exaggerated to make it a little bit simpler.
yeah,
In this
because
case, it's 150 meters, right? So
yeah,
it means you have nearly 10 meters wavelength. So it means in this case, you are investigating the uppermost 5 meters,
yeah,
more or
because
less. Okay.
yeah, because we can see the figure below of the 14 hertz, it's very shallow, and in that shallow range, we have less variability of the
Mhm.
velocity. And the next question is related to
So,
the
but
source.
of course, don't misunderstand me. When we calculate, then the velocity profile here, we have a full dispersion curve. So we are not using only 6 and 14 hertz, but we
Mhm.
use also the frequencies in between.
Oh,
No?
okay. Oh,
So
okay.
this is just an example to show you some, let's say, extreme cases from the very shallow to the deepest part that we could use. Of course, you can also use all the frequencies in between, and that's what we have done.
Okay, like the 6 hertz, 7 hertz in the form of stepwise, then we use the best results where we have best match, right?
Yes, you have to do it exactly like, I mean, it's like what you can do, for example, you can also look at the frequency content of your correlation and you see where you have signal, no? Where you have
Mm.
enough signal when it's enough good. So you can select the frequency range where the, let's say, the signal is still enough strong to be observed and you can measure the velocity. It
Yeah,
can be that with this distance, when you go to higher frequency, you are not able anymore to estimate the velocity. Or when you go to too low frequency, the wavelength is becoming too large with respect to the dimension of array. And of course, you will not see the propagation in this method.
when,
Everything will be homogeneous. You know, such a long wavelength will see everything
yeah,
as homogeneous.
yeah. My next question was related to like if we go for the regional scale, we have different sources of the noise. So what is the parameter we have to I mean look for the range of frequency. If some region have low sources of noise, so then what frequency range we could I mean test for the inversion.
It's difficult to tell you what is best. When you go to regional scale, you will have a lot, you will work a lot in the low frequency and mainly in the frequency range of a microseism that can be,
Mhm.
like we said, 0.1, 0.05 hertz. There you have a lot of energy generation. But it depends strongly on where is your network, which data are you including, because of course, if you are closer to the coastline, you will have more high frequency also entering in the game and so on. So there is no, I wouldn't say that I would say that there is no rule of thumb in this case that can really tell you what you can observe in your data. And also, especially for the low frequency, you will need more and more stacking, more data, no? While for the high frequency,
Yeah.
like we are doing here, that's working in 20 minutes because of course, yeah, you can sum up a lot of signal at 20 or 14 hertz in 20 minutes. But if you would have a 0.05 hertz, it's very few cycles that you are stacking, you know.
Yeah.
So
Yeah.
you need maybe 1 year
Mm.
of data when you go to regional studies, or at least a seasonal level, so you can see also some
Mm.
seasonal changes. So months of data sometimes are necessary in order that you can obtain stable estimations. So it's like if you have a very complicated signal made of many things, many sources, everything is chaotic, let's say. You have a lot of things depending on many paths that are
Mm.
recorded, depending on different source and so on. But among all these signal, there is always the signal that is propagating between the two sensors, okay?
Yeah.
This ballistic part, we can call it. And what you're doing when you correlate and you stack, you try to remove all these signals which are randomly coming,
Mm.
and you enhance, you can see
That
it in
place.
this way, you can enhance the one that is always propagating between the two sensors.
Yeah.
Maybe this is very weak and at the beginning is masked by all the other signal, you know,
Yeah.
but with time and stacking, it's the only one persistent. And that's what you are trying to get out of this, in this way.
Yeah. Okay.
It's just a simple way to explain it.
Yeah,
Just
I
you know,
understand.
without
Yeah.
mathematics, is just to tell you how you have to visualize this in your mind.
Yeah, I understand. Thank
Okay,
you.
you're welcome. Is there any other question? Okay, then for today, I will show you a couple of simple things, and then I would like to start more on the buildings and things tomorrow. I would like just to tell you that we studied mainly side effects in linear field. So we were mainly considering that the site response is not depending on the input ground motion. But we know that, for example, if the input ground motion can become large, also the soil can change behavior. So our transfer function will depend on the input. So the soil can behave non-linearly. There are some extreme cases also of side effects when the nonlinearity is becoming, let's say, extreme, that are very relevant. And in the past, probably they have been a little bit underestimated in the sense that we were expecting this to be more rare effects and mainly related to only to very large shaking. But we realize with last earthquakes that they can also happen to smaller ground shaking that we were expecting in the past. So the earthquake in New Zealand, Christchurch, the earthquake in Emilia-Romagna in Italy a few years ago, they show very large effect, extreme nonlinearity that here is described as liquefaction. And even the recent earthquake in Croatia, probably you heard about it just after Christmas and before New Year's Eve, these generate a huge amount of liquefaction. So why we have liquefaction? And the liquefaction, you can see the effect here. No? Generally, we have buildings with foundations. And what is happening is that the soil on which the building was founded is really liquefying. It's becoming like quicksand. So the building is not able to stand anymore. And you see here, maybe not even really damage, I would say, by the shaking, but completely gone because of the liquefaction made the building tilting and collapsing in this sense. So why is this happening? This is happening generally because we can have some material, principally can happen in sands, but not only, that are, this material is saturated, is water saturated. And so we have some fluid, some water in the pore space between the grain, let's say, of sands. And especially this is a problem when the sand is not really well graded. So there is a lot of space in the pore and a lot of fluids. What is happening is that when the shaking becomes large and lasts for a lot of time, you have pore pressure increase. If the pore pressure is becoming larger than the effective stress, then the material is really becoming like a sort of quicksand. So you see the grain are pushed apart. And what can happen is that you can have this material coming up at the surface, given the sun boils, or in other cases, on very small or very small slope, for example, you can have what we have ground failure. So the ground can really open with large fractures that can be also very deep, sometimes large as 1 meter and deep or a few meters, that are causing huge amount of damage. Other typical example of this strong nonlinearity, you have it from the 1964 events in Alaska. So if you watch some figures of Anchorage, all these ground failure that you observe is not the fault. The fault that generated the event was quite far away, but it's mainly ground failure related to liquefaction. Even the earthquake here in Alaska generated a huge amount of liquefaction. In that case, the pore pressure was increasing because, you know, the soil saturated material that liquefied was just below, for example, a frozen layer of material. And below this frozen layer, so the pore pressure is not able to dissipate anymore. So you have a large increase here and then it's liquefying. And in this way, we also explain some earthquakes in Central Asia that happened more than 100 years ago. So looking at the images and comparing the damage or what's happened for similar shaking of another event that didn't generate liquefaction, we could prove in a way that the large liquefaction that the earthquake in winter generate was due to the fact that the soil was frozen and didn't allow the pore pressure to dissipate. So this is a very important event, effect. So you see also here, so generally you have the cyclic shear is a compaction of grain, then we have a pore pressure increase, and the pore pressure increase is making the, which is increasing here, is making the effective stress to decay until you can have a full liquefaction and large problems in the ground. What is interesting is that there are very few recordings. Now it's a bit increasing, but to have a sensor which is collocated to places where you have liquefaction is not so, let's say, it's not happening so often. And it is interesting, for example, to see what could be the effect of this pore pressure increase and liquefaction also on the shaking that we are measuring at the surface. So these are the surface, you see at 0 meter, and the boral acceleration time histories for the Kushiro-Oki earthquake of 1993. And what is really amazing in this recording is this alternance you see here of spikes, sort of cusp, that are happening in this very last part of the recording for the surface recording, but that you, of course, do not observe in the boral, where the shaking is also much smaller, like we would expect from all what we are studying on side effects. So, and this sort of behavior seems to be related. Some studies show that this could be related to the compaction of the material. So you have liquefaction, then due to the shaking, the material compact again. So the stiffness is increasing for a very short amount of time. So you have a spike, and then due to the continuous shaking, you have the material, the grains, again, separating and then compacting again, generating this very large spike. So this is really still one of the most complicated things also for the simulation. Of course, we have tools also for simulating liquefactions, but these tools are requiring, of course, a huge number of parameters that we can only approximate in the numerical simulation when we want to cover an area. So very often we cannot make a study so detailed in each place where we are building, because we need a lot of parameters, and depending on the code and depending on the description of the medium that you have, the changes can be also significant. So the first effect that I show you of liquefaction was more or less related to this. So you have a soil here that is becoming, it's liquefying, and therefore also your building can lose bearing capacity below the foundation. Or as I mentioned before, if you have just a small inclination, a small slope, as soon as you have liquefaction below, let's say, for example, river banks or areas close to river banks, then you have an opening of fractures here because one part is moving away of the river banks and generating very large ground failure. So there are tools, generally liquefaction has been studied a lot, especially by geotechnical engineers, and a lot with lab analysis. So for example, using three-axis cycles apparatus or cylindrical sample of soil. So generally you see the apparatus here, you put the sample of soil, which is a small sample that should be undisturbed, is brought to a sort of confining pressure. And then for a certain pore pressure, you start having vertical compression and extensional cycles of a certain amplitude. So you start compacting and compacting it. And n that you have here, or as a function of time, is giving you the number of cycles. What you observe is that it takes quite a lot of time before the pore pressure is increasing. And before that, the actual deformation is rising. So it's not only important for the liquefaction, the amplitude of a shaking, but it's also important the duration of a shaking. So how many cycle is the sample or the ground undergoing before it's reaching liquefaction? So this is the standard method that is used a lot in geotechnical analysis. The problem is that you need samples, and sampling can be costly, and also the experiment in the lab is costly. And then you need also what is called undisturbed samples. So you should be able to sample the material without disturbing its original structure, which is of course not so easy. Nowadays, there are also some techniques to freeze the sample and to disturb it as less as possible. The other point is also how realistic could be such a kind of experiments where it's done on a small sample, while we know that, let's say, the wavelengths we are talking about when we are discussing earthquake shaking can have tens of meters of dimensions, so can have a different impact also on the soil. But this is generally what is done. So of course you can also use approximated methods in order to have some information about the liquefaction over a certain area. So there are two important factors, if you want to do it in this way, that are generating liquefactor. The first one is how a certain soil is susceptible to liquefaction. So if we have a certain soil that we know is not going to liquefy very likely, I think some kind of clays, for example, so you have a low susceptibility. Of course, to have liquefaction, you should have something which is susceptible to it, but you should also have an external factor that is the loading action. Loading action on the ground that depends on the ground motion. And that's always or very often defined as opportunity. So it's the ability of a certain earthquake to generate, to cause at a certain distance the liquefaction. So liquefaction opportunity, it's considering liquefaction in most susceptible soil. So if we combine the susceptibility and the opportunity, then we have the liquefaction potential or liquefaction hazard. So this is what we can do. So just to tell you what are the important parameters for susceptibility, so the characteristic of the material. So density, it's very important. So denser, for example, is the sand, the lower is the probability of susceptibility. High confining pressure. So if you have a high confining pressure, it will be less probable for the same increase of pore pressure that you will have a liquefaction. Over consolidation ratio, so the more is consolidated the soil, lower its susceptibility, and also the kind of granulometric curve that you have. So cohesive soil, like clays, they are low susceptibility. Granular material with few fine content can liquefy. So these are some standards, but then you can also enter more into the geotechnical analysis, and you can define, depending on granulometry, depending on certain parameters which are typical of geotechnical engineer, define if more or less a clay soil or a silty sand or a sand can liquefy. And also, it's very important, the granulometric curve. So this diagram is just telling you what is the size and the range of size of the grains in the material. So if this curve is spanning along, let's say, along this horizontal direction, it means you have a very different grain size. If it's all constrained moving in the vertical direction, let's say, it means you have grain size very similar. And this, especially in this range indicated here, is the range where you expect generally larger liquefaction. So I will not enter in all the description of liquefaction, but just to tell you that generally susceptibility can be defined, for example, from very simple observation and very simple geological characterization based on the fact that we know that we can have more liquefaction on all the riverbed, swamp, medium possible liquefaction on fan, natural leaves, sand dunes, and not likely liquefaction on terrace, hills, and mountains. Or you can enter a little bit more into details, combining a more refined geological description, considering the age of the deposit, and also considering the distribution of the cohesion of the soil. Generally, we have high liquefaction, you see marine terrace, fan delta, lacustic deposit, and so on, where you expect also high water content. Otherwise, you couldn't have liquefaction. And okay, and this is the same for other kind of information. Okay. Do you have questions about this?
I have a general question.
Yes.
That is not related to, there was an earthquake in Pakistan in 2019 with magnitude 5.6 in Mirpur. It occurred, at 200 kilometers from the dam.
Yeah.
But the deformation is mostly close to the dam, but not exactly close to it, was far from like 10 or 15 kilometer, but there was a gap where we do not observe any deformation. So is it possible if we are near the dam and there is there is some kind of no deformation, then we observe deformation from uh, I mean away from this that I mean distance, there is a no deformation in 10 kilometer and there is we observe deformation that was
More
extreme.
far away. So you had
Yeah,
more. Okay, I don't know exactly the earthquake and I don't know the geology there where you talking about, because this is, of course, would be important
yeah,
to be
yeah.
known. But generally speaking, yes, what can happen is that maybe, let's say, the earthquake is happening in an area where you have mainly, let's say, rock sides, but more far away, you have an area with swamp. I'm just imagining, no, or with sediments that have a high susceptibility, and therefore, with a shaking, even if they are more far away, you have a large induced liquefaction and maybe ground failure that is giving you a lot of deformation. This can happen because you have changes in the local geology that can induce this. So in one of the earthquake, maybe I have it here, I will go a little bit. This is really an example I was talking before. You see, this is an earthquake, for example, that was happening 20 kilometers from Verni, which is Almaty nowadays. It was 1887.
Mhm.
Was a very large earthquake. It was a magnitude 7.3, which
Mhm.
induced some liquefaction, but very small and only very close to the river. And all the rest was large damage in the construction of the time. In 1911, there was an earthquake that was stronger, but was also more far away. And if you look at the big ground acceleration, they are more or less compatible in the terms of shaking that we expect. But in this case of this earthquake, the amount of liquefaction was huge. And you see it here, you see this ground.
Yeah,
These are just, you see there is a man here. So
yeah,
just to, I show you just to tell you how strong it was. No,
yeah.
and this was a devastating effect of ground failure. You see, this is 40 kilometers from the fault,
Yeah.
at least, and you had this large ground failure and liquefaction all over the town. In this case, this was induced by the fact, as I was mentioning before, this earthquake happened in January, the earthquake before in July. So we assume, and we made some numerical simulation, that in January here you have 1 meter of frozen layer. So
Mhm.
in June, July would have been possible for the pore pressure to dissipate, because you have also some gravel material and sand. In January, it was not possible because the frozen layer was like a seal. So just at the bottom of this layer, all the pressure was increasing until
Mhm.
when it liquefied, and then you start having this effect of big fading. So, and then you see, you had the greatest amount, not in the mountain area, at least as we know, but in this area because you have a river, you have a material that was prone to liquefy and so on. So this can be spotted depending on where the geology is changing.
Yeah. And there are also similar kind of deformation. There is also a shared kind of deformation. We have multiple, I mean, cracks
Yeah.
near to the canal and and dam,
Mm-hmm.
and then there is a gap, and then again this type of deformation.
Yes. Yeah, I see. No, it's really important. As I mentioned, very often in the past we didn't consider too much, and still also when we are calculating hazard, we are mainly focusing on the shaking, no?
Yeah.
But it's becoming more and more also in the engineering seismology community, more use also to start preparing also probabilistic hazard map for liquefaction, because of course it's a very important factor. but one has to take into account also in design. It's not only the shaking creating problems.
Yeah, exactly.
Okay, if there are no other questions, we see tomorrow then. It's correct?
Yeah.
Yes.
And diploma students can tell us if
Sorry?
there. I'm saying that diploma students can tell us if there is any change.
Ah, okay, yes. Okay, we'll save this and then, okay, if there is no any other thing, then we will see tomorrow. It's fine like this?
Okay.
Yeah.
Okay. Bye-bye.
Yes.
Ciao.
Thanks.
Yeah,
Bye.
bye.
Ciao,
Bye.
Mariella.
Bye.
Ciao, ciao.
Tomorrow. Bye.
Bye.
Bye. Ciao.